I would like to present our recent results on the blowing up solutions of a system of fractional differential equations. It is a joint work with my current PhD supervisor, Professor Mukhtar Kiran, as a part of my PhD thesis contributions. So in this talk, I would like to give an overview of our recent result. Sorry, excuse me, I need to move this one. It's a bit, okay. About our recent results on the following research paper without going into too much of the details of the explanation of the calculation. So if during my presentation, one of you would like to see more into the details of the calculation, I welcome you to go to visit our paper instead. Hopefully that by skipping some of the details, I would still be able to deliver what is the idea on the research. So in our problem, in our research, we are interested to analyze the following system of nonlinear fractional differential equation with power nonlinearities. Here, the powers a, b, p, q are assumed to be greater than 1. The power of k1 and k2 will be determined later, and the derivative under consideration is the fractional derivative in the Caputo sense given by the following definition. Without the loss of generalities, we assume that alpha is less than or equal to beta. Essentially, it's just what we want to say is that one fractional order is simply less than the other. It could be the same, but in general, it is different. So if you allow me, I would like to highlight why in the first place we consider the fractional order settings to our system rather than the usual classical order settings. Well, we claim that with the fractional order settings, we'll be able to describe the evolution or the dynamic better than the usual settings. Why? Because simply from the equation, if the usual derivative usually measure the rate of change of an object at an instantaneous time t, while the fractional order derivative will allow us to take into account the accumulation of that object rate of change until certain times t. Well, multiply by some weighted kernel here. So using the fractional derivative, it will allow us to have a better precision because at every time t, we're taking into account the historical behavior of that object. But we see also that from the definition, the kernel here is singular, weakly singular, but singular also. So by weakly singular, I mean that by one time integrating, the singularity disappears. It is no more singular. But still, this kernel of the weakly singular type usually poses a different challenge when we want to do our analysis. So it comes two parts. The model is becoming more accurate, but it comes with a price of the presence of these weakly singularities that we need to tackle. But now you might ask me why this problem per se, why this right-hand side per se? Is it just cooked to get our results in our paper? Well, actually not really. So the equation, see, if we take only one equation here, that equation has been studied by Midlargic to model the rapid temperature rise in the shear band formation of steel. So if I may give you a little bit of an idea of what it is, that if we have an object and that object made of steel, for example, and that object is placed under a continuous strain or stress, then eventually that object will break. Now that deformation is usually accompanied by the rapid change of the temperature of that object at that point. So what we're trying to model here is actually the rapid change of the temperature, the dynamic of the temperature. If we can identify under which condition that the temperature would suddenly rise up, then we can identify under which condition also the deformation will occur because of this link between these two. And in fact, in the shear band formation of steel, Midlargic considered this following Volterra integral equation, which is actually equivalent to the following fractional differential equation with alpha equals to 1/2. Now, one might ask, if we have an object and that object is made not only from steel, but also from a combination of steel or some other things, then what would be the behavior? We propose the following model. And the alpha doesn't need necessarily be 1/2. In the case of the steel, it is 1/2. But what about the other? So by considering the more general case, we will be able to detect more of material deformation that can appear later in nature. More for the application wise is that the equivalent integral form of our system is of Volterra type, and the Volterra type equation has been used to model the system that may exhibit an explosive behavior in a diffusive media. Now you may ask that in our system there is no diffusive term, right? There is no diffusive, you see no Laplacian, no P Laplacian, no fractional, nothing. So our system can actually be seen as the same system that exhibits the explosive behavior in diffusive media, but the analysis is done in highly localized, specialized region. And moreover, Su also highlights the use of the fractional derivative in modeling the slow and uncertain oxidation process of copper, noting its similarities to combustion processes. So usually in combustion, rather than having this power type nonlinearities, one would also incorporate the exponential type nonlinearities. But by approximation, you can go back again to this power type nonlinearities. And also, if I may add a little bit, that our type of nonlinearities can be seen also as a prototype of the results of the mass action law. So if you can come into a system that comes from this mass action law, then the results in our research can also be applied to those systems. But that is from the application point of view. What about the previous results in a mathematical results? So before Midlarczyk, Okrasinski, and Robert considered the following Volterra system look alike our system, but here they take as the power of the kernel n and m. This n and m is an integer. There they present the bilateral estimates of the blowing up time and the growth rate of the blow up solution near the blowing up time. Now, the analysis for the fractional case, the fractional power alpha and beta, is studied by Professor Mokhtar and his collaborator. There they take the case A, B, K1, K2 to be equals to 0. If I may go back a little bit. So yeah, they consider the following non-linear right-hand side, but only this part without the presence of this this part. So there they provide the necessary conditions of the existence based on suitable test function. And later on, Professor Mukhtar and his PhD student, Dr. Salman Amin Malik, they completed the analysis and they obtained the bilateral estimates of the blowing up time and the profile of the blowing up solution using the nonlinear capacity methods of Pokhozaev. Later on, Professor Kirk, Olmsted, and Roberts takes the model of Professor Mukhtar and his students and extended, studied that system, provide an alternative way, and compare the results to the results of Professor Mukhtar and his students. Now, before we dive into our results, I would like to go back to actually the classical settings. And I would like to see what is the behavior of our system rather in a simpler format. So again, I'm really sorry if I may go back here. Let us consider this alpha and beta to be equal to 1. And without this presence of K1 and K2, take K1 and K2 to be 0 here. In fact, when K1 and K2 are the same, then we can rescale a problem. Then we can have only this powers as our right-hand side. So consider the first simplest case of our classical settings is by taking this part to be constant, so our system is completely decoupled. By taking A and B to be greater than 1, if our system is provided by the positive initial data, then we know that the solution to the system will blow up in finite time. And the proof is extremely easy. By the usual separation of variable method, we can compute the solution. And here we know that the solution as t goes to this tu and as t goes to tv, u and v will blow up. And what about we consider the coupled system? So now this part will be constant and this one not, this one, right? So also by the standard method in the ODE, provided with the positive initial data and the power P and Q to be greater than 1, we can decouple the system. And we can show that also the solution blows up in finite time. Now, what about a slightly more complicated one, that it is the system is fully coupled? So we denote by lambda to be the interaction between the power of u, and mu is the interaction of the power of q. We say that if lambda and mu doesn't compete in sign, and in the case when lambda and mu is negative, this extra condition is satisfied. I'm really sorry, it should be u0 and v0. Then the solution of our system blows up in finite time also. And this result is actually achieved by, again, trying to decouple the system, solving the first integral curve, and then we will arrive at our blowing up results in the classical settings. Can we do it in the fractional setting? Absolutely not. There is no known results up until now that can decouple the fractional order system. So we need another tools to arrive to our blowing up solution. So before we prove the existence of the blowing up solution, first we need to show the existence of positive solution to our system. And it is quite procedural, but I would just go briefly for the sake of completeness. So the first step we need to do is that we convert our differential system into the system of integral equation of Volterra type. And then we consider the Banach space of continuous functions, since we're looking for a continuous positive growing solutions. And by Banach fixed point theorem, we will arrive at our local existence, means that there exists a time t such that our solution exists. Now this t is the t of the Banach fixed point theorem. It might differ from one person to another, but then we need to find the maximal possible time possible for our solution to exist. We denote by Tmax such time, meaning that the maximum time of existence. We show the alternative is either Tmax is infinite or Tmax is finite, and our solution goes to infinity as t goes to Tmax. In the case Tmax is infinite, we say that our solution global, meaning that the solution exists for all time. And in the case when Tmax is infinite also, we notice that our solution might be bounded or might be unbounded. For example, if we say that our solution is exponential growth, it exists at all time, but it is unbounded. So sometimes to show the existence of the blowing up solution, it is not enough for us to show the existence of the continuous growing solution. We need to still show the blow up. But anyway, after we denote this this Tmax, we establish the uniqueness of our solution in the whole interval time of existence by utilizing weakly singular ground wall lemma. One can choose, there are many versions, but one can choose one that is suitable to their needs. And in our paper, we show which one is ours. So the next thing to show is that in our case, that it is really the latter part of the alternative holds, meaning that Tmax is indeed finite, and in our case that the solution goes to infinity as t goes to Tmax. So here we characterize under which condition the blowing up solution occur. Again, we denote by lambda and mu. Lambda is the interaction between the power of u. Mu is the interaction, lambda is the interaction between the power of x, and mu is the interaction of the power of y. If K1 and K2 is satisfies the following condition, and lambda and mu doesn't compete in sign, and when it is negative, it satisfies the following condition. So if one of this condition is satisfied and K1 and K2 satisfy the following condition, then the solution indeed blows up in finite time. Also, when K1 and K2 equals to 0, then also our solution blows up in finite time. So I'm going to give only the proofs for the first part. It is quite short, quite easy, just only the sketch of the proof, and the rest is the same. Not really the same, but the idea is the same. That is by using the comparison method. Maybe the comparison between one condition and the other is not the same, but the idea is there. So we introduce the following change of variable. Let u be t plus 1 raised to the power of 1 minus alpha x, v t plus 1 raised to the power of 1 minus beta y. By doing the following change of variable, we see that u and v will be greater than this following quantity. Now, by our condition on K1 and K2, we see that our solution to the fractional differential system is actually an upper solution of the solution of the following classical order system, which we know from our preliminary analysis that the system of this, the solution of this system blows up in finite time. So being an upper solution, it means that it is bigger than if the solution of the classical sense already blew up. The solution of this classical sense kind of pushes the solution of the fractional order system. And there we arrive at our blow up condition. And now, not only it is important for us to characterize under which condition our system will exhibit a blowing up solution, but also when the solution will blow up, because essentially in practice, one would want to make an intervention so that the blow up doesn't really occur. So it is very hard to get a blow up time estimate for, especially for this coupled nonlinear system. But if we have at least the estimate, the upper blow up time estimates way before this, something needs to be done so that the blow up doesn't occur. So we know that the solution will blow up as a certain critical time T max. So we say that under the hypothesis of the previous theorems, the upper bound estimates for the blow up time T max is given by the minimum of the 6 quantities over here, which interestingly, or maybe not so interesting, that of all these 6 quantities, there is no alpha and beta appear here. No alpha and beta at all. Then one might ask me, well, Sofwah, you claim that by changing the system by using the alpha and beta as the fractional order to describe your evolution, you say that you will gain a better understanding of the system. But now here it seems that it plays no role at all. The alpha and beta doesn't appear. Well, one might even ask me a question that from where you got this 6 estimates. Well, I will answer the second question first, because actually the 6 estimate, just as the proof of the previous theorems that I showed you, that our solution is actually an upper solution of the system of the classical settings. I show you only one condition, but actually if you go through our paper, then you will see that the solution of our fractional settings is actually an upper solution of all possible cases that I showed you in the classical settings. And this one is actually the upper blow-up time estimate for the first system. This one is upper blow-up time estimate of the second system. This one is upper blow-up time estimate for the third system. Being bigger than the solution of our classical settings, it means that our solution must have blown up faster than our classical settings. But still, then we remain in the first question, where is the role of alpha and beta here then? Because it doesn't show here at all. Well, the role of alpha and beta will come in the precision of the behavior of the blowing up solution near the critical time. So here, as t goes to t max, we know that our solution blows up. So as t goes to t max, x will goes to infinity in the following rate, and y will goes to infinity in the following rate. And this rate, alpha and beta, appear here. Not only in the power, but also, whoopsie, yes, but also in this coefficient here, which is quite extensive, and I do not expect anyone to remember. I myself do not even remember all this, but we know that it exists. What is interesting for us to know is that how to get to the following estimates. The answer is by moving to the complex plane. So first of all, I would like to give some tools that we need to have before we move to the complex plane. In fact, we will move to the complex plane using the Mellin transform. So just to give the definition here, which I will recall later on. So the Mellin transform of a function f is given by this integral, and the integral is defined in the following strip. And one of the properties of the Mellin transform that we shall use is this one, the scaling properties of Mellin transform. And we move from the real domain to the complex domain by the Parsifal formulas for the Mellin transform. So it says that the product, so the integral of the product of two functions by the Parsifal formulas, it moves to the complex domain by the multiplication of the Mellin transform of the product of both functions, which with some sort of involution here. But this is the tools that we will do. So again, here I will give only the sketch of the proof, hopefully that I do not miss too much of the details here. So the first step that we need to do is to provide the change of variable. From our previous results, we already see that there exists a critical time such that as t goes to t max, x and y goes to infinity. We introduce the following transformation eta. So as t goes to t max, eta will goes to infinity. Now by performing the following change of variable, we will be able to see under when eta goes to infinity, our function will also goes to infinity. So it will free ourselves from dealing with fraction. Now the growth rate near singularity will be analyzed using the asymptotic analysis method established in Blystein and Handelsman. Maybe one thing that I would like to notice here, at least this one as a student, I appreciate it very much. I don't know really if it is there already in literature, but this asymptotic method by Blystein, it allows us to provide the growth rate of the singularities even without knowing exactly where is Tmax. The analysis still goes. So I don't know. For me, it is really interesting, and it's even more interesting when I see how do they apply it, so that I can apply it here. So for the sake of simplicity, we denote by sigma is our fractional order derivative. This is also the power of our kernel. And kappa 1, kappa 2 is just our kernel of integration. And this R and phi, this R and phi is simply our right-hand side. our right-hand side. And then, as usual, we work with the integral formulation, right? This is just our initial condition. This is our kappa, and this is our right-hand side. Now, we perform a further change of variable such that this quantity over here, it is nothing but the results of the change of variable. Now, we are interested to analyze the following integral equation as eta goes to infinity. So for large eta, the contribution of the initial value actually is not really it's not really important. So we can just analyze this wj eta as the integral. So this qj here is the integral, and I throw this eta out. So yeah, this qj, again, that this phi is our right-hand side. Then the next things that we can do is that we can stretch from 0 to 1, the domain of integration, to 0 to infinity by simply multiplying by the Heaviside function. And this k is simply just kappa multiplied by some Heaviside function, and this f is our right-hand side. See, this f is just r times phi with some, how do I say, the extra variables coming from the change of variables. Now, the next step to do is to move to the complex plane by applying the Parsifal formulas and the scaling properties of Mellon's transform. So we apply the Mellon transform of the singular kernel, and then this one is our right-hand side. And lucky for us, then now we can deal with our weakly singular kernel by just simply computing this Mellon transform of weakly singular kernel, which is this one. It's a bit ugly. Cut it here, but let me move it here, right? So if we look at this following integral, we notice also a problem here. Why? Because we notice that this part of the integral, it has some singularities, as we know that gamma has singularities at every non-positive integer. So at z equals 1, z equals 2, z equals 3, and so on, then this part has the singularities. Now, what about this part? Will this part kill the singularities? Will this part have singularities also? If so, then how would they interact? So we need to also analyze this one, obviously. But to analyze the Mellon transform of f, we also need to analyze the behavior of f itself as eta goes to infinity. Now we see that as f goes to infinity, this f has a behavior of power type nonlinearities for this eta. Hence, we assume that our solution, actually this wj eta, assume also the power type nonlinearities. And if blow up does occur, if we substitute this 27 to here, then we substitute it here to the whole integral equation, then it must give an asymptotic power balance. If it's not, then it's wrong. So yeah, so let's first substitute.
I have a problem. I don't see the screen. Do all of you see the screen?
Yeah, I see, but I don't know what.
Oh, okay, fine.
Yes, sir.
Go ahead, Sofwah. It is my own.
Oh,
yes.
In your computer, maybe. Okay.
Maybe re-sign in, sir. Sorry.
You can see also.
Okay.
There's no presentation.
Yeah,
Same
so,
here, Sofwah, I can't see the screen, so it is just saying Zoom.
Zoom, yeah.
so no one see my screen?
No, everything is fine.
Oh, everything is fine. Okay, okay. So shall I continue? Yes.
Yes.
So yeah,
You would like to show the presentation or the
yeah,
browser? We don't see the presentation, we see the browser.
Really?
Yeah.
All this time you're not seeing the...
No. Before it was okay. Now you are sharing your screen. Now, yeah. Now, okay.
Now, yeah. Am I?
Now, okay.
Now, okay. Yeah. So when I go to this part, it was okay. Yes. Hello, sir. Sorry. Shall I continue?
Probably yes.
Yeah.
Yes,
Okay.
it's okay.
Yes.
Okay. It's okay. So I was saying that we let Wj eta to assume this power type of nonlinearities, and when we substitute it to 26 and then 25, we shall we shall get the asymptotic power balance. So first of all, we substitute it here to 27 to 26. We obtain the following format. We obtain the following form. And then the next thing that we need to do is to calculate the Mellin transform. Just to recall that the Mellin transform of a function is given by this following integral. If we substitute this f1 or f2 to the following integral, we see that the integral doesn't exist. It simply can't exist. So if I call this, let's focus only on the first equation. If I call the first power of the equation as z1, then the integral will only exist at the left part of z1. Then what does it mean? It means that z1 is the point of singularities of our Mellin transform of f of 1. Then what to do next? What to do next is to extend. So by doing the analytic continuation, we can characterize the type of the singularities of Z1 and Z2. It turns out that the type of the singularities is a simple pole, so that we can express the Mellin transform of F1 and F2 to be of this form, and we substitute it to our integral, which I shall move here for a better clarity, right? So again, we see that in this case, in this part, we have a singularities of a pole type, and this one also gamma exhibits singularities at every non-positive integer. Then what to do next? The next step that we need to do is we impose the restriction to take Z1 and Z2 to be less than 1. I'm really sorry, I didn't say which one, Z1, Z2. This is the Z1, and this is Z2. We impose the restriction. By imposing the restriction Z1 and Z2 to be less than 1, then the singularities of Z1 and Z2 will be encountered before the singularities of this one, which is 1. The first singularities of gamma that we may encounter is 1. So if this one is encountered first in the integral before this one, then this part of the integrand will provide a dominant contribution for the entire integral. And then we can use the Cauchy integral formula just to analyze it at the integral as at z1. And there we have our expression for the eta and the coefficient. We say that before that if it does if blow up does occur, then our proposed power nonlinearity type should provide the consistent asymptotic power balance, meaning that we equate this one with the coefficient of W1 and this one with Wj. So it is exactly just this. All right, so we need to solve these two. And then also for the asymptotic power balance of the power itself, we need to equate these two. Then by solving the system, we have the results of the growth rate that we have before. Of course, we test our results by the numerical scheme. Here, I only provide you with one how do I say, with one graph. But in our paper, we show that in all possible cases of our results, our solution indeed blow up, and it indeed blow up before the upper blow up time estimate. So what's next? So what's next? Of course, we may extend, rather than considering our problem with only alpha and beta between 0s and 1, we may consider a variable order derivative depending on time, when alpha is now alpha t and beta is beta t, when alpha t and beta t is between 0s and 1s. We may also consider a more general right-hand side. So in this F and G, we may put other type of nonlinearities, exponential, logarithmic, and their combination for the sake of mathematical perspective. But I would like to also see, so we subtract the system, the generalized system, by the following quantities, because essentially when we have the blow up, the derivative of our solution also, it is infinite. So one might ask that if we subtract our system due to the sum power, so which power of S and R here that would essentially stabilize the system? So this could be the future possible direction for research. And also, as I mentioned before, that the system actually come from the natural questions that model the, how do I say, the environment with the potential blowing up or explosive behavior in the diffusive medium. Now I want to incorporate the diffusion term, but in diffusion term I would like to add the fractional diffusion term, where sigma and gamma here is between zeros and ones. F and G assume any other type of nonlinearities, and also the subtraction here is the same, right? So in the case of fractional diffusion system, that the singularities might happen t goes to certain t star, or x goes to certain x star also. So it might also lose singularities, lose regularities in the gradient. So by subtracting this one, again, making it more powerful by multiplying by u to the power of s, v to the power of r, then what values L, S, and R will stabilize the system. Also, I can put this ut here and then ut multiply by, so all this possible future direction. So of course, the first one is our paper. You are more than welcome to see more of the detailed calculation in our paper. And this book of Bleistein and Handelsman will give you an idea on how to get the expansions. And from the third one, this paper by Shadams and Pierce, it will allow you to see how to move from the system with the diffusive term into only the system of differential equations. And also the following are the paper of Professor Mokhtar and his collaborator, from which we compare our results to. And the numerics you can see from this Li and Zhang. And at least, yeah, I think that's it from me. If anyone has a question, I would be more than happy to discuss and answer.